Hello there. Today we are talking about effect size. Effect size is important to psychology for two reasons. The first is that it gives us a measure of how easy our effect is to see. Or to use it in its own definition, it gives us the size of the effect. So when we're talking about effect sizes, we have a spectrum, a continuum. We have things with very small effects and large effects. Let's go with swimming. So when we're talking about small effects over here, we could talk about shaving before a meet. That's just one of the things in swimming, as you typically shave before your large meets, so you reduce your drag, you increase your hydrodynamic properties. And by reducing drag, you see small improvements in your speed. Nothing major, but you do see an improvement. On the large end, let's just call it training. If we were to take somebody who hadn't trained but shaved, they might save a couple seconds on, let's say, a 500-yard race. If we took someone who trained but didn't shave, we would see them take potentially minutes off that 500-yard race. And so this would have a larger effect size than this would. They both make a difference. They're both there. They're both real effects. But this one is much more obvious than this one. And so effect size is helpful in giving us a measure of where an effect falls between a small and a large. Things that are difficult to see and things that are blatantly obvious. Now, the second reason effect size is important in psychology is that it is one of the essential components of power analysis. Now, before we go any further, we need to talk about how we calculate our effect size. And thankfully, it's fairly simple. Whoop. There we go. So, effect size is typically denoted with a lowercase d that has been bolded. Sometimes it will be called bolded d. Though more commonly, it is called Cohen's d. This is after Jacob Cohen, who's arguably the most famous statistician in psychology. There are a couple arguments to be made, but he's arguably the most famous, though maybe Fisher is more famous or Neyman and Pearson, but Jacob Cohen is right up there. Now, how do we calculate it? Well, thankfully it's fairly simple. Cohen's d is equal to mu1 minus mu2 over the standard deviation of the population. Very simple, very, very simple. Now, let's say that we are looking at, let's say gummy bears. And in this study, the population 1, so let's go, mu1 is equal to, let's say 37 in a day, whereas mu2 is equal to 83 in a day. And typically, well, first, let's go into this. Typically, we would orient mu1 and mu2 so that the larger one goes first, just so we're dealing with positive numbers. It's just a convention that makes things a little bit easier to keep going in our head, and we don't have to worry about negative signs. So let's go ahead and swap these around just so that we can continue to deal with positive numbers. And that our standard deviation is equal to, let's go 13 again. So if I have two different populations, where am I getting a single standard deviation? Well, the answer to this is that this version of the formula is for the same standard deviation. So we're making the assumption that these are just subsets of a larger population. So let's say that these people who eat gummy bears live in zone 1 and zone 2, and that zone 1 and zone 2 both exist in country A. And so that overall we have the same standard deviation, and so we're just taking the standard deviation for country A. However, this isn't always the case. It works for this when we do have that work, but it doesn't work when we don't have that. Now we could just take our two standard deviations, add them together, and have a pooled, we don't use this notation, but we could have this, and we say, well, 1 plus 2 divided by 2 is equal to our standard deviation pooled. We don't do that. You'd end up with a somewhat accurate estimator of the standard deviation, but if we really want to do this, we really need to take the harmonic mean. We really should just take the harmonic mean. So, when are we going to talk about harmonic means? Well, it's a fairly in-depth discussion, so that will come in a future presentation, probably in the next couple of days. But for now, let's just go with what we have. So we're taking mu1 and mu2. Well, so that means we have 83 minus 37 over 13. Let's pull out a good old calculator to save all the extra brain power. 83 minus 37 is equal to 46 over 13. 46 divided by 13. Whoa, hold on there. 46 divided by 13 is equal to 3.54 with rounding, and that gives us our answer. So this tells us that the effect size we're seeing comparing population 1 and 2 is very large. And let's go up here to this chart we had to begin with and plug in what we typically see. So on the small end, we see a small effect is typically classified as 0.2. So this is our small effect. 0.5 is seen as a medium effect, and 0.8 is seen as a large effect. So having an effect size of 3.54 is massive. It's so large as to be obvious. Now, as we go back up here, there are some gray areas in saying, well, it's a small effect size below 0.2 and up to 0.499. As we've discussed before, there's not all that much of a difference between 4.99 and 5.00. It's just a distinction we have. And so there is some gray area in where we say a medium effect begins and ends. Is 0.7 really a medium effect? Or is 0.78 a medium effect when it's so close to a large effect? And where you go with saying, well, it's a very large small effect, or it is a large medium effect, or it's a small large effect, and going in and making that distinction that best represents the data, I'd say the best ground rule here is to see what people in your field do for similar effect sizes. Though this is a generally accepted guideline that you can follow, that anything under 0.2 is small, and anything from 0.2 to 0.5 is also small. 0.5 to 0.8 is medium, and 0.8 and above is a large effect. Other places you could go to check this are faculty in whatever program you're attending. They will be able to give you an indication of, do we follow exactly this sort of standard template, or in what we're seeing is that 4.99, are we just going to call that a medium effect because it's closer to a medium effect than it is to a small effect? Regardless, effect size is an interesting topic. I hope that this outline has been useful for you, and that if you are dealing with a situation where you have two different standard deviations that you need to use, that you will go and check the video on the on the harmonic mean, instead of just using this more error-filled version of taking the average of the two standard deviations. And just to reiterate, this is not common terminology. I don't think you'll see anybody who knows this. They might be able to guess at what it means, but this is not standard, just something I made up on the fly. So don't go using it. All right. Hopefully this is helpful for you. Let me know if it has been, and if you have any questions about what I've covered here. And until next time, cheers.